get data and how we can organize and summarize data with tables and graphs. So the first type we're going to look at is known as a frequency distribution. It's really good for large data sets, but the only problem with frequency distributions is that you lose the actual original data values. You just have an interval. You just know that there are a certain number between here and here. There are two types of frequency distributions. One is an ungrouped frequency distribution, and it's best for qualitative data. And you can see an example of that in table 2.3 in your textbook. Or a grouped frequency distribution, which is good and used for quantitative data. You can see an example of it in table 2.4. I want to go over the procedure on how to do a frequency distribution for a grouped frequency distribution for quantitative data with you now. So the first thing you want to do is you want to list all the data values along with their corresponding frequencies. Now to do this, the first thing you need to do is decide on the number of classes you want. Usually you want a number between 5 and 20. Anything less than 5 and you haven't grouped enough. Anything more than 20, if you've grouped so much that you're not benefiting from the grouping. Another rule of thumb can be the number of groups should be approximately the square root of your sample size. These are all just guidelines, not hard and fast rules. To calculate the class width, you can use the maximum value minus the minimum value and then divide by the number of classes you've decided on. You should then round up to get a nice number. Like if I had a number like 4.2, I would round up to 5. 5 is a nice number. If I had a number like 12, I would probably round up to 15. 15 is a nice number. But these are guidelines, right? There's no hard and fast rules here. Begin at or below the minimum value. This will be the lower limit of the first class. Now add the class width to this lower limit repeatedly to get all the subsequent lower limits. Use these lower class limits to get the upper class limit so that they are right up to each other but do not overlap. They touch but do not overlap. Then you can just use tally marks to determine how many data values are in each of these classes. There are different types of frequency. There's a relative frequency, which is equal to the number in the class divided by the total number in the data set. And this can be represented as a decimal, a fraction, or a percent. You have cumulative frequency, and this is the sum of the frequencies of that class and all previous classes. And you can also make both relative and cumulative frequency tables. So for example, let's look at this. So here we have our classes. So this class goes from 60 to 63. The lower class limit is 60. The upper class limit is 63. My class width is the difference between two subsequent lower class limits or two subsequent upper class limits. The difference between 60 and 64 is 4, but so is the difference between 67 and 71 or 68 and 72. So we took our class width, we added it to get all of these lower class limits, and then we looked for the number that went right up to 64 but did not overlap it. So that was 63. And then you just counted the frequency of the numbers of men whose heights were between 60 and 63. In this case, there were 2 men whose height was between 60 and 63 inches. I just showed you a minute ago, so what do you think the class width for this frequency distribution is? That's right, it's 4, because 64 minus 60 is 4. What's the relative frequency of the third class represented as a decimal? When you look at the third class, you're going to take the frequency from class 3 divided by the total. In this case, the frequency for class 3 was 9. There was 20 values in our sample, so 9 divided by 20 is 0.45. What's the cumulative frequency of the third class? Recall, to get the cumulative frequency, it's the frequency in that class and all previous classes. So you're going to add together the frequency of class 1, class 2, and class 3, and you get 2 plus 5 plus 9 is 16. So the cumulative frequency for class 3 is 16. This is a graphical representation of a frequency distribution. It's a type of bar graph and it's drawn with no gaps whatsoever. The horizontal axis represents the classes of data values and the vertical axis represents the frequencies. So this is an example of the histogram for the frequency distribution we saw just a minute ago, or the heights of men. The relative frequency histogram is very similar, except instead of using the frequencies on the vertical axis, you use the relative frequencies instead. And if you notice, the shape of this histogram is the same as the shape of the histogram that we saw a minute ago for the frequency histogram. The difference is the values that are on this vertical scaling. A frequency polygon uses line segments just to connect the tops of the histograms. So the heights correspond just to the frequency. It's saving all the ink that we use to draw all the bars. Now the line extends to 0 at the right and at the left. So at the end, you start at 0, and at the end, you finish at 0. But it just puts a dot, so it still tells you the shape of the data without using all the ink. It's more common in a more academic journal than a histogram is more common in a more popular journal. You can see the text for examples of a frequency polygon. An ogive is similar, it's only that it uses the cumulative frequency and you do not return to 0. The dot plot. A dot plot uses a scale, a horizontal scale for all our values, and each dot represents how many points lie on that, in that value. I'm not a big fan of dot plots, but you can see examples of them in your book. The stem and leaf plot is more common. The left units are either the tens, the hundreds, or the thousands, or the stems, and then on each, the units are the leaves. A Pareto chart is a bar graph for qualitative data. So it's the same thing. Now, bar graphs do not have to touch, but they can touch, whereas a histogram must touch. A histogram is a bar graph for quantitative data, and a bar graph is only for qualitative data. And a Pareto chart is a particular type of bar graph that goes from the smallest to the largest. And a pie chart, most of you are familiar with pie charts. Pie charts and bar graphs are the two most common types of graphs used for qualitative data. It's what you saw in high school when you graphed points on the Cartesian coordinate system. You have data in the form of x and y. It's known as bivariate data. So each sample point is two values are taken, for example, height and weight. And then each data point is plotted on the graph. So for example, suppose I have these values, and then I put these in. So 2333 would be this point right here, 2536, that point right there, and so forth, 16 and 41. Right? So most of you are very familiar with how to graph on the XY coordinate plane. Now, scatter plots can be used to determine correlation. Correlation exists if one variable is associated with another variable. For example, if our waist circumference is associated with our arm circumference, and there's a linear correlation if when we do the scatter plot of the two variables, the pattern is approximating a straight line. We're going to see a lot more of this when you do Minitab Lab 2. I've given you another recording that has to do with Minitab Lab 2. Minitab Lab 1 should be done first. It's a very easy lab to do. There's really nothing to turn in except I think there's one question on it. Other than that, the rest of it is just learning how to enter data values in and how to use Minitab. But lab 2 starts our first real lab, and it'll be doing all these different graphs. You're going to be looking at some stem and leaf plots, some histograms, and so forth. So as you do these mini-tab labs, you can you'll get some practice looking at all these labs. Graph is another bivariate graph, except that in this case, all of the x values correspond to some time. Time could be days of the week, hours of the day, months of the year, or years. And then the y value is the value that we're measuring at that time. So suppose I was doing temperature throughout the day. So I was dealing with a patient who had a fever. So I did a temperature reading once an hour from 8 a.m. to 8 p.m. So at 8 o'clock, the first x value would be 8, and the y value would be their temperature. Let's say it's 102.3. Then the next x value would be 9 o'clock, so it'd be 9. And let's say their temperature now is gone up a little bit, it's 102.7, and so forth. So each x has at most one y value, and you can see the trend in time. The data values are then connected by line segments, and you get an idea of what the trend is over time. Now, there's different shapes of data. Symmetric data means if you folded the graph down the middle, the left half is roughly the mirror image of the right half. Examples of symmetric data are the bell-shaped curve and uniform data. The bell-shaped curve kind of looks like a bell, and uniform data looks like a rectangle. We're going to be seeing more of this when we get to chapter 7. And then we have skewed data. Now data can be either skewed right or skewed left. Skewed right data means that, let me see, we'll have most of the data here on the left side and the tail is on the right. And on skewed left data, we have the tail is on the left and most of the data is here on the right. Skewed right data is things like income. Most of us are down here in our income, and there's a few very rich people over here. They make up the tail on the right side. Skewed left data, an example of that would be life expectancy. A few people die young, but most of us die up here. So that's life expectancy. We're going to see in chapter 3 what the mean and the median are, but I'm just going to point this out now. When you have skewed right data, the mean will always be greater than the median. It's another way to determine if your data is skewed right. And if it's skewed left, the mean will always be less than the median. And it's another way to determine if your data is skewed left.